Math 110, review number 1. So this video is just basically introducing some of the important concepts that we should know going into this class. Knowing how to manipulate equations algebraically, examining graphs, finding domain and range, understanding at least somewhat of these concepts, you're going to see how this is going to filter in through the rest of the concepts that we go over in this math class. So being able to be good at these is going to be really important. And so this is going to be kind of like a brief overview of some of these important concepts. And if you ever have any questions, please just know that you can always ask them. You can comment in the video, or you can ask me in class. So the first that we're going to go over is, and this is in a portion of your book, it's called the just-in-time. And this is going to be number 6. And basically, we're going to talk about interval notation. Now, the idea here is how do we translate a mathematical statement into interval notation? Interval notation is much easier to represent, it's much easier to understand, and it's much easier to read, and it can be a little bit quicker. So there's a few things to kind of qualify here. The first is going to be this symbology here, this greater than or less than. We call these excluded values, and the reason why we say that is because it can be everything up to that value, but not including that value, and that's why it's excluded. And so the way that we represent that is by parentheses. Greater than or equal to, these are included values because we can actually include that value as well. And I know this seems a little bit abstract, but I'll talk about it in the examples. But as you can see here, I have we represent that with brackets, and then infinity is always going to be represented with a parenthesis. And the reason is we don't know what infinity is. We just know it's some impossibly large number, and negative infinity is some impossibly negative large number. But we don't know exactly what it is. The moment that you say infinity is this number, I'm going to add 1 to it and prove you wrong. So it's not a defined value. And so because it's not defined, we don't know what it is, we signify that with the parentheses. So let's look at our first example. We call this set builder notation, and usually we have some sort of dummy variable here, and then it's going to tell you what that variable represents. And so this is saying that x is between -5 and +5. And so sometimes it helps us to kind of visualize what that looks like. And so what this is saying is that x is between -5, so -5 is the smallest value, +5 is the largest value. Now because these are included values, I represented that with brackets. And so notice here I have a bracket here, and I have a bracket here. And so now being able to translate this into interval notation, this is going to be from -5 all the way to +5. And so I just start with that first value that I see here, and then I end with the last value here. And so this statement represents that I'm saying everything in between -5 to +5, including -5 and including +5. So look at another example here. This says x is between -3 and -1. Now -3 is excluded, +1 is included. And so representing that, this is like an open circle because it's excluded, but I also can signify that with the parenthesis. And since I'm including the -1 closed circle, I'm writing that with the bracket. And so being able to translate this is going to start at -3 with a parenthesis, go all the way to -1 with a bracket here. And then the last statement here, it's going to be x such that 7 is less than x. And so visualizing that, 7 being less than x, basically it's saying x is going to be, has to be larger than that. So the region that's larger than 7 is going to be my result. So it's going to start at 7, and x has to be everything larger than that. And so to be able to represent that, that's going to be from 7 to +infinity. Now this next one, we're going to be examining exponents, and so these are all the different properties of exponents that we could be using. So the first properties here, we have the product rule. This says that when we multiply exponents with the same base, you're going to add them together, so you're going to add those exponents together. when we're dividing these powers with the same base, you take the exponents and you subtract them. And then for this one, we have powers and we're taking it to another exponent. You multiply those two exponents together. And then you could also, in the same rationale, if you imagine this, there's being like a 1 here and a 1 here, you take that m and you multiply it with both of them. And so 1 times m is m, and so that's why it's a to the m times b to the m. So those are just a couple of things to visualize there. And then also, there's some basic rules. The first says anything to the 0 exponent is going to be 1. A to the negative m power. This is going to be 1 over a to the m. So the idea is that if you ever have a negative exponent, you can flip it over the divisor. If you imagined like this a was over 1, if you can take that entire power there and flip it over the divisor, and by doing that you can make the exponent go from positive to negative or negative to positive. And so this is another visual representation of that, is if I flip both of them, notice my b is going to be a positive n and my a is going to be a positive m. So my first example here, examining this, I have 4 squared times 4 to the negative 5th. Well, this is going to be the product rule, and so my bases are the same, and so because my bases are the same, I'm going to add the powers together. So I'm going to get 4 to the negative 3rd power. Now because of this rule here, a to the negative m, that means I can take this and I can flip it over the divisor. So this is going to become 1 over 4 to the 3rd power. And then I can simplify that further and say that's 1 over 64. Example number 2, I have 7 over 9 to the 0 power. And so we said anything to the 0 exponent is going to be 1, and so that's going to be 1. For this power here, I have this power to this exponent, and so 8 squared to the negative 5th. We're going to be using this property here called the power rule. And so what I need to do now is I need to multiply those two exponents together. And so this is going to be 8 to the negative 10th. And so now we go back to this basic rule here. Whenever I have a negative exponent, I can flip it. And so I get 1 over 8 to the 10th. Now this is like somewhere where we'd use a calculator to kind of help us and simplify, but just know that that's sufficient. Example number 4, whenever we're dealing with powers and the bases are the same and we're dividing here, you're going to subtract the powers. So this is going to be x to the 11 minus 4. And so I simplify that there, and that's going to give me x to the 7th power. Example number 5, this is another one of those rules where I have this to some sort of power, and so that power is going to go to both of them. Imagine if there's like 1s there, and so that's going to be a to the 3rd and then over b to the 3rd. And example number 6, if I imagine this c and d both have to the 1st power, this negative 2 is like almost being distributed with both, and so I get c to the negative 2nd, d to the negative 2nd. Then I can go back to this basic rule here. This is going to get flipped over the divisor, and so I get 1 over c squared d squared. Now just in time number 9, this is going to be order of operations. So this is kind of like the order in which we go through and we simplify or evaluate expressions. And so we first want to start with grouping symbols. Then we go to evaluating exponential expressions. Then we do multiplication and division from left to right, whatever is first. And then addition and subtraction, left to right, whatever is first. Now I understand that we have this PEMDAS stuck in our brain, and so it's like we go through and look at it almost like a checklist. That is incorrect. We have to consider multiplication and division universally the same thing, and so we're going to examine that from left to right first together, and then addition and subtraction together from left to right. So for this one right here, if I do 5 minus 3, the first I need to check for is grouping symbols, and so this right here is being grouped together, and so 5 minus 3 gives me 2. Then evaluating any exponential expressions, this is 2 to the 3rd power, and so 2 to the 3rd power is going to be 8 because 2 times 2 times 2 is 8. Then 8 times 8, that's going to give me 64 minus 20, and that's going to give me 44. There was multiplication right here, and then addition and subtraction right here, and that's how I get 44. Example number 2. Now one thing that kind of helps us with this is we have to envision this top and this bottom being separately grouped together. Whenever you see divisors like that, and they might not be written in that there's parentheses, you assume that there's like some sort of parenthesis there. And so now let's look at this top one first. Maybe I'll do both of them at the same time. But grouping them together, I have this grouping symbol, so I can do that first. So 8 minus 6 is going to give me that 2. Everything else stayed the same. It's still 10 divided by plus 9 times 4. And then down here in this grouping symbol, I see exponential expressions. So 2 to the 5th is 32. 3 squared is 9. So now, still within this group, I don't see any exponential expressions, but I do see multiplication and division. I need to do this one first from left to right. And so this one is going to give me 5, and then this one is going to give me 36. And then I don't see any multiplication or division here, but I do see addition and subtraction. And so adding those together, I'm going to get 41. And so now the only thing I have left on top is adding the subtraction. So adding those together, I get 41 over 41, which is just 1. Now on this one, we're going to be adding and subtracting polynomials. Now this states that if two terms of an expression have the same variables raised to the same powers, they're called like terms or similar terms. And we're able to combine them and collect them together using the distributive property or just simple addition and subtraction. So in this example here, I need to find what type of variables are the same. And so in this case, this negative 5x to the third and this 12x to the third are the same. And so you just add or subtract the coefficients. So negative 5 plus 12, that's going to give me 7x to the third. I know that this 3x squared and this 7x squared, those are the same. So 3 plus negative 7 is going to give me negative 4x squared. This negative x, there's no other x term. I can't combine it with that. So I just have negative x. And this 3, there's no other constant, so I can't combine that together. So I get plus 3. Now with example number 2, we have to examine terms that have the same powers together. Those are considered like terms. So this is the term x squared y to the third. And I can only combine that together with other terms that have x squared y to the third. The other thing that we should examine is the fact that this is subtraction. Now because this is subtraction, we're going to be allowed to distribute that through. And so that becomes negative 5x squared y to the third, and negative is a positive 4xy. So now combining like terms, this term and this term are the same, so 6 minus 5, that's just going to give me 1x squared y to the third, which is the same as x squared y to the third. And then negative 9xy plus 4xy, that's going to give me negative 5xy. And that's going to be my answer. So this one here is just in time number 12, which is multiplying polynomials together. Now, to multiply polynomials, you first multiply their coefficients, then multiply their variables. So in this case, negative 2 times 5 is going to give me that negative 10. Now multiply the variables. X to the third times x to the fourth. Bases are the same, so you add the powers. And so that's going to give me x to the seventh. Example number 2, you can have a bunch of variables. You can have a bunch of these numbers in front, the coefficients. Doesn't matter. First, multiply the coefficients. So 3 times 8 is going to give me 24. Now my y's. Now this is y to the first power. So 1 plus 3 gives me y to the fourth. And then z squared times z to the fifth. That's going to give me z to the seventh power. Now sometimes we have this special type of multiplication. This is a binomial and this is a binomial. Now I'm sure you've heard the word FOIL, but FOIL is just a special form of distributing the variables. The way that we look at it is we take the first term and we're going to multiply it with the next two. So 2x times 3x, that gives me 6x squared. And then 2x times 4, that's going to give me 8x. So since I multiplied this with both of these terms and got those, now I move over to the next term. So now it's negative 7 times 3x, which is minus 21x. Negative 7 times 4, that's going to give me negative 28. Now to help you remember that, they say FOIL, first, outer, inner, last. But just understand that it's a form of distributing, and all you're doing is you're taking this first term and you're multiplying it with the next two, which is what I had here, taking the second term and you're multiplying it with these two, and that's how I got those two there. And so after we multiply everything through, combining like terms, 6x squared, 8x minus 21x, that gives me negative 13x, and then minus 28. Now example number 4, don't let this deceive you. I know we talked about exponents and we thought, oh, we just take the square and we distribute it. That can't be applied here because of that plus. This is saying I have two 4x plus 1s. So I have two of these. So then this goes back to our distributing. And so the first one is 4x times 4x gives me 16x squared. Then the second one, 4x times 1, 1 times 4x, and then 1 times 1 gives me 1. Combining like terms, I'm going to get that 8x. Now when we're factoring polynomials, there's going to be various layers of factoring. The first is going to be factoring the greatest common factor. And so what we need to do is we need to look at all of our terms and we need to say which factor, the largest, is going to be in common with all of them. And so out of 15, I know my factors are going to be 5 and 3, 5, 2, and x, 5 and x and x. And so out of all those factors stated, the largest one in common is going to be 5. And so because there's a 5 in common, I can write this 5 on the outside, and it's like I'm dividing every single term by 5. So 15 divided by 5 is 3, plus 10x divided by 5 is 2x, and then these 5's cancel out, and so I'm going to get minus x squared. And so this right here is going to be my answer for that. Now, when we factor by grouping, this is going to be another form of factoring, so we're going to be going over like 3 or 4 ways. GCF here, factor by grouping, typically there's 4 terms. And the idea here is what we're going to do is we're going to kind of divide this equation in half here. And when we divide this equation in half, I'm going to get this x to the third plus 3x squared. And then on this side, I get this minus 5x minus 15. What we're going to do is we're going to do this whole GCF form of factoring on each side of this divided line. So what's in common here are 2 x's. So I'm going to say x squared. And so now it's like I'm dividing both of these by x squared, and so I'm going to get x, and that's going to be plus 3. Over here, there's going to be a negative 5 in common, and so I factor out the negative 5, and so negative 5's cancel out, and I get a positive x. Negative 15 divided by negative 5 gives me that positive 3. Now, an indicator that we did do this right is going to be the fact that these should be the same. If they're not the same, it means one of two things. One, we did it wrong, so we need to go back through and double check ourselves. Or two, you can't do it. We can't do the factor by grouping. So it means one of two things. So we want to make sure that these are the same. Now, once you know that they're the same, you just rewrite one of them. Okay? Because the idea is now between these two terms, we have an x plus 3 in common. And so I factor out that x plus 3, which is here. And so what you're going to have left is this x squared and this minus 5. And so that's going to go into the other parenthesis. And so that's going to be my answer when I factor by grouping. And so now we're going to be factoring a trinomial. When we're factoring, we're going to have to write it a series of multiplication. I know this is showing up. This is for a different problem. We'll get to that soon. So don't let this affect what we're doing here. But when we're factoring, we have to examine it in the form of ax squared plus bx plus c equals 0. Now, factoring a trinomial means there's 3 terms. 1, 2, 3. I like using the greatest common factor, the factor by grouping method. We multiply a times c, and we put that on top. We write our b on the bottom, and in these 2 spots, we look for the factors of a times c that are going to add to b. So in this example here, A times C, 1 times 6 is 6. My B is 5. I'm going to put my B here. So I need to think to myself, what are the factors of 6? And I can write them out. 1 and 6, 2 and 3. Which one of those are going to add to 5 and still multiply to that 6? Well, I can do -1 and -6 and -2 and -3 because negative is positive. So it ends up being this possibility here. And so because of that, what I can do is I can say I now have this x squared and then plus 2x plus 3x, and then I still have this 6 on the outside. And so now you're going to do factor by grouping. And so you're going to say here what's in common, it's going to be x. What's in common here is going to be a 3. And so now that those are the same, yay, you did it right. And so you're going to get x plus 2, and then x plus 3 is going to go in the other one. So you're probably wondering, wait, how did we get from this to this? What happened there? Okay, so let me review that again. So what I did was I took the x squared, that stayed the same. What I wanted to do is I wanted to break apart this 5x into these factors here. So how did I get these values here? 2x and 3x. So I got those two values there. And so the plus 6 is still there. So the only thing that changed in this expression here is this 5x. So I took this 5x and I rewrote it as 2x plus 3x. And that's going to be my answer. So let's look at another one. Now, one of the things when we're factoring trinomials, one thing that we should always examine first is a GCF. Is there a factor in common that I can factor out first? And so in this case, there's actually an x squared that's in common with all of them. And so I want to factor out the x squared. Now that it's in this form where it's a trinomial because I factored everything out, now this right here I can factor it. And so once again I do my x box method. I do a times c, so 1 times 8, that's going to go here. My b of -6 is going to go here, and so I need to figure what factors of 8, so what times what gives me 8, will then add to -6. And so in this case, -4 and -2 are going to add to that -6, -4 and -2 multiplied to the 8. So this is just a way to represent your information. So now I want to break apart this 6x into this -4 and this -2. And so I broke it apart. Instead of writing -6x, I'm writing that -4x, which is from here, and the -2x, which is from here. And so now this is just factor by grouping. And so I factor out the x, and I factor out the -2. And so if I factor out -2, I'm left with x minus 4. And so I do have this x minus 4 that's in common here. And then I have the x minus 2, which is here. And then my x squared is still left over from the problem here. And so that's going to be my answer. Now another form of factoring is going to be the difference of squares. And the way that we're going to do this is we want to find the formula, or we're going to use the formula for that. So when it comes to this one, a squared minus b squared is going to factor into a plus b and a minus b. Now this is something that we kind of want to memorize. It's going to be so much easier if we do memorize it to kind of visualize and see what's going on there. And so the phrase difference of squares means difference minus of two perfect squares. And so if you notice, it's just the square root of each of those go into those spots here. So the square root of a squared goes here and here. The square root of b squared goes here and here. And you just write it as a pair of binomials, one with a plus and one with a minus. And so for this one right here, difference of perfect squares. And so my a in this case is going to be 2y. My b in this case is going to be 3. So a plus b, a minus b. And that's my answer. Now some of these, it might require further factoring, and so let's examine this. In this case, my a is x squared, my y is b squared. So a plus b, a minus b. Now this one is also a difference of squares. And so my a in that one is x and my b in that one is y. So this is still the same, but in this case it's going to be a plus b and a minus b. And so I was able to factor that further, and so that's going to be my answer. Now the last one, the difference of cubes here, we could follow this formula. Once we take the cube root, and the cube root, we just plug it into this formula and we have our result. I like to sing a little song. This kind of helps me when it comes to memorizing this. You guys might like this too. But the idea here is once I find what the cube root of this is and the cube root of this is, it's going to be much easier. So find that. So the cube root of a cubed is going to be a. And then the cube root of 8z to the third is just going to be 2z. And so when I use the phrase first times first and my first and last and stuff, I'm going to refer to this. This is the first and this is the last. And so the song goes, first times first is first, last times last is last, first times last is in the middle, isn't this a blast? The first sign's from the problem, the second's it's reversed, the last sign's always positive no matter what the first. And you're done. It's been factored. And just to me, that's so much easier than going through all of that. So just kind of like a recap on that. First and last from the song, you just need to take the cube root, and so this is going to be that first and last that I'm going to use from the song. And it goes first times first is first, last times last is last, first times last is in the middle, isn't this a blast? The first sign's from the problem, the second's it's reversed, the last sign's always positive no matter what the first. And then you're done. Let's try another one. So for this one here, take the cube root, so the cube root, it's like we're dividing that by 3, you get squared, and then that's how we get our y squared. And so once again, this is first and this is last, and so going through the song, we're going to say first times first is first, last times last is last, first times last is in the middle, isn't this a blast? The first sign's from the problem, the second's it's reversed, the last sign's always positive no matter what the first. And it's been factored. And so hopefully this will kind of help you when it comes to difference of cubes. Now the way that you, this could be sum or difference of cubes. Sorry, this should have been phrased sum or difference of cubes. But the idea here is that whenever you see a plus or minus of two perfect cubes here, we know that we're going to be able to factor it, and using this song might help. And then if we remember here, this x squared minus y squared, this is now a difference of squares, and so I can factor that further using what I did for difference of squares. Now we're going to talk about solving equations, and so the first is going to be the add and subtracting principle. And so it basically says that I can add and subtract a number from both sides. And then we also have the multiplication principle that says that I can multiply a number to both sides. So in this first example, if I have y minus 11 equals 12, to get y by itself, I want to add 11 to both sides. And so the negative 11 and a positive 11 will cancel out. And so 12 plus 11, that's going to give me y equals 23. On this one here, I'm going to divide both sides by 15. And so I get c equals 6. Now you're probably wondering, wait a minute, I didn't talk about a division principle. Well, division and multiplication, they're very similar, because if I say divide by 15, that's the same as multiply by 1 over 15, right? Those are the same thing. And so that's why I can divide both sides by a number. And so 90 divided by the 15 gives me c equals 6. And so sometimes we're going to have to combine multiple of these principles together, like a bunch of them. And so I can distribute this negative 6 through. And so if I do that, rewriting it, negative 6 times x is negative 6x, negative times a negative is a positive 6. So now on both sides I want to combine like terms, so this 1 and the 6 combine together. And now that I have terms on both sides, I can bring all the x's to one side. And so I'm going to add 6x to both sides, bring all the numbers to the other, so I'm going to minus 3 on both sides. So 2x and 6x is 8x. 7 minus 3 is 4. Then divide both sides by 8, and I get x equals 1/2. And then we also have the zero product principle. Now the way that we do this zero product principle is if I know that a times b equals 0, I can make the assumption that a is 0, b is 0, or both of them is going to be 0. And then it also works backwards. If I say that a is 0 or b is 0, then I can also say that both of those multiplied together is going to be 0. So when it comes to this factoring, this is actually going to help us when it comes to factoring or solving equations, especially when it comes to these trinomials, because if I can represent it as a series of factors, I can then solve it. So for this one here, I want to factor it. A times c is -4, b -3 on the bottom. So the factors that are going to add to -3 multiply to 4 would be -4 and 1. So I can break this -3x into -4x and 1x. Factor by grouping, go through and do it. I know I'm going to go kind of quick on this. But now for this this principle zero product, I can take, because I know if I say this is 0, then it doesn't matter, that's going to be 0. If I say that this is 0, then it doesn't matter, this entire thing is going to be 0. So I set each of those equal to 0. So I'm going to add 4 to both sides, I get x equals 4, subtract 1 on both sides, and I get x equals -1. And so this is going to be my answer. Now on example number 2, for this one here, factor it. A times c is going to go on the top, b is going to go on the bottom. And so what times what is going to give me -6, that's going to add to 5. And so I can break this apart, this 5x into a positive 6x, and this -1x. So now factor by grouping, what's in common here is 2x, what's in common here is -1. And so rewriting this, I get the x plus 3 and then the 2x minus 1, and that equals 0. And so now I set each of these equal to 0 because of the zero product property. And then -3 on both sides, I get x equals -3. If I add 1 and divide by 2, I get x equals 1/2. And so that's going to be my answer for that one. Now we have the principle of square roots. All this says is that if x squared equals k, then x equals the positive square root of k, or x equals the negative square root of k, meaning I have to include a plus or minus whenever I take the square root. So here, if I add 144 to both sides, I'm going to get s squared equals 144. So if I take the square root of both sides, I have to say s equals the positive version of that and the negative version of that. And so s equals plus or minus 12. For this one here, I add 21 to both sides, so I get 3x squared equals 21. Then to get that x squared by itself, divide both sides by 3, and I'm going to get x squared equals 7. Take the square root of both sides, and so I get x equals plus or minus √7. So that concludes this first half of the review. So if you guys have any questions, please leave them in the comments.